So let me motivate why we think CMB observations are potent observables for the era of reionization. So after recombination epoch, the CMB photons traveled unhindered till they encountered the free electron population in the reionization era, and this would modify the temperature and polarization anisotropies of the CMB photon population. The three main observables in this regard is the Thomson scattering optical depth tau, and we have heard in the previous talk a lot about it. The second is the kinetic Sunyaev-Zeldovich effect, which is basically when CMB photons, when they scatter off ionized bubbles with a net bulk velocity, they have a Doppler shift associated. So that would modify the temperature anisotropy. And the third one is when the CMB photons inhomogeneously scatter through the free electron population, they gain E and D mode polarization. So E and D mode are basically the two bases in which we can break the polarization vector, and reionization produces both E and D mode polarization. So why is this important? So we have three potent connections between CMB reionization, CMB and reionization. We already have measurements from Planck and SPT team on the optical depth tau and the KZ signal. And what we'd like to understand is if it can tell, if these integrated quantities can tell something about the open questions of reionization. Basically, when did the first stars form, or how fast was the process of reionization? Was it patchy? Was it not? So these questions. So we have observations. So in order to infer about the process of reionization, we would like to have a simulation which can generate these observables. And in this regard, we use script. Now, script is an explicitly photon-conserving semi-numerical scheme of reionization, which helps us generate ionization maps. So the basic idea is you provide script with a dark matter snapshot at redshift. Script operates with two variables regarding the ionizing sources. That is the minimum mass at which the halos can host ionizing sources and the ionizing efficiency of the sources. And at the end, the script would give you an ionization map. So from this ionization map, you can compute various observables of interest. And in this regard, we are able to calculate the optical depth tau, the KSZ power, and the patchy B mode power. But this is not all. So we would also need a way to a model which will try to constrain, which will tell us about how these ionizing sources evolve with redshift. And in this regard, we use a power law over redshift for the Mmin and the ionizing efficiency zeta. The Mmin naught and zeta naught are basically the minimum mass of halos and the ionizing efficiency at redshift of 8, while alpha m and alpha zeta are the power law index. So the whole idea is we have this model of reionization. When we specify these models, these four parameters, use MCMC sampler and let it vary through the free parameters of this model. It would give us the CMB observables of tau, KSZ, and B mode power, and we can compare that in the likelihood function, and we'll get constraints on these four parameters, and in return, we'll also make constraints on the process of reionization. We additionally have placed prior in this regard through previous studies. It is accepted that the reionization should end by redshift of 5, and additionally, we have placed these priors, physically motivated priors on these free parameters. So we have these four free parameters. We define the tau chi-square and the KSZ chi-square based on the observations of Planck and SPT, and the constraints we get are as follows. So these are the four free parameters of the model. The most important I would like to point is currently we see that the Planck plus SPT data prefers a log m min naught at redshift of 8 to be slightly greater than 9, this would suggest that at redshift of 8, probably star formation is suppressed at lower halo masses as a result of radiative feedback. And also, the alpha zeta parameter, that is the power law index for the ionizing efficiency, comes out to be negative, which tells us that probably the ionizing efficiency of the sources is increasing with redshift, and this is probably due to improved cooling and star formation in these sources. We are also able to make constraints on the reionization history, like the midpoint of reionization, the 75% end of reionization, and the duration of reionization. And further, we are also able to make constraints on parameters which are associated to the patchiness in the process of reionization, that is the KSZ signal at multipole of 3000 and the B mode power at multiple pole of 200. And we see that the CMB observables have taken us this far regarding constraints of reionization history. Once we have 21 centimeter measurements, we believe that that will help us tighten the allowed reionization history space. So in that context, once we have 21 centimeter observations, probably we'll see more tighter constraints on these parameters. For our model, the best fit came out to be the following, and the corresponding to that best fit, the B mode power we achieved was at multipole of 200 was around 7.03 nanokelvin square, and for a model which is allowed by the 3 sigma contours, which has the highest B mode power, the power came out to be at 18.41 nanokelvin square. The natural question for us was to understand immediately if this B mode power that arises as a result of patchiness in the process of reionization may impact our future observations of the tensor-to-scalar ratio R. To set the context, so after the Big Bang, it is postulated that there was a phase of quasi-exponential expansion, and primordial gravitational waves are a common feature for these inflationary models. Now, the primordial gravitational wave would imprint a polarization signature on the CMB, and the amplitude of this polarization signature is quantified in terms of the tensor-to-scalar power spectrum ratio R at wave mode of 0.5 megaparsec inverse. We already have constraint at 95% confidence limits by the Keck collaboration at 0.036, and we would want to we want to constrain this parameter R through future CMB observations. But this is challenging because the most dominant contribution comes from our own galaxy through galactic synchrotron and the polarized thermal emission into the B mode. And also, the large-scale structures would lens the E mode polarization from CMB to B mode polarization. And finally, we have the B modes coming from the patchy reionization process. So what we would like to understand is if patchy reionization can act as a foreground to our inference of the primordial gravitational wave signature. In order to do so, we construct a mock power spectrum, which constitutes of 3 quantities: the B mode primordial gravitational power spectrum, the lensing contribution to this B mode, and this patchiness and patchy reionization contribution to B mode. So these 2 quantities can be calculated through CMB codes like CAM. And so once you specify the delensing ability of the telescope with just the parameter tensor-to-scalar ratio R, you can compute this primordial power. And in order to generate the mock power spectra, we use the patchy reionization power, which was allowed for the best fit model, which was constrained for the Planck plus SPT data. So in order to test the inference bias on R, what we do is, so this is our mock power spectra. We choose 2 models. In one model, we include the effect of patchy reionization power. In another model, we leave out the patchy reionization power term. And we have 4 parameters of the reionization, an additional parameter which would help us get the primordial gravitational wave power. And what we'd like to know is if we try to infer the parameter R for these two models, what is the difference between the mean of the inferred posterior? And we can quantify this estimate by dividing this with the significance with the standard deviation of the posterior for R. So what we did was we combined the 3 observables of tau, KSZ, and B mode, and we because Pico will make the most sensitive observations of B modes. I'll just talk about the case where we are in a situation where we have projected observations from Lightbird tau and CMBS4, and Pico will make the B mode power observations. We see that if in a case where we have 100% delensing, that is, lensing does not contribute, we see that the case for which template without the reionization power, a higher R is inferred. This is intuitive because in that model, we have left out the contribution from the patchy reionization. So we infer a higher value of R. But this deviation from the true inferred R is very significant. And for that, the bias goes at 1.59 sigma. But this is not a realistic case. Pico will try to reach the delensing ability at 85%, and by the allowed instrumental beam sensitivity of those experiments, that can go theoretically at delensing of 95%. And with for R of 5 times 10 to the power minus 4, we already see that Pico will observe a bias of 0.23 sigma and 0.31 sigma if it fails to account for the patchy reionization contribution to the signal. Why this is important? Even though these are not, the numbers are not significant, but what we, for a confirmed detection, we would want a 5 sigma detection of R. And if we have an incorrect model of reionization, if we have if someone is claiming 5 sigma, then probably we are losing out. So we'll have a lesser sensitive detection at 4.8 sigma or 4.7 sigma. But this case worsens if we choose a model of reionization which was allowed by the Planck plus SPT data, but at 3 sigma contours with maximum patchy B mode contribution. And for that, we obtain the numbers of, I'm sorry, this is delta R. So the delta R is 0.43 sigma and 0.73 sigma. So this tells us how not accounting for the patchy reionization process in modeling of the B mode power spectra is really impacting the tensor-to-scalar power spectrum ratio R. We have seen that CMB observables are very potential probes of reionization and has allowed us to constrain the ionization history. 21 centimeter measurements will significantly constrain the ionizing histories allowed by the current measurements. And if we neglect the B mode contribution to the total model of B mode power spectra, will bias the measurement on R. And so in future, combined data set likelihood would help us to understand more about the reionization process and also potentially mitigate any contamination to the tensor to power spectrum ratio R. Thank you.
Thanks, Divesh. So, question for.
So, when you have a drift or bias of this magnitude, maybe a more rational approach is instead of subtracting your reionization contamination, you marginalize over it. Have you considered this? And then the question would be, in that case, does the central value of the posterior drift or not? And if it doesn't, then one would be able to advocate that as the better procedure for future experiments. Have you looked into this at all?
So this particular posterior, we have for this black template, this corresponds to a model where we have already included all 3 contributions, and this is the marginalized posterior over R. So Yeah. Sorry.
So the SPT and Planck inference hasn't gone into this, or
It has so no Planck inference and SPT. Only the best fit model was used to create the Mach spectra. But I used this combination of experiment, the Lightbird, CMBS4, and Pico.
I see.
So we have the projected noise for the Lightbird tau and the CMBS4, and we try to
yeah, that's
check the
the right
bias for
thing to
Pico.
do. That's great. Yeah, thank you.
Yeah, maybe a very naive question. When you combine your Planck tau and the SPT, you are not using the cross terms covariance. You are just using the sigma square, the error on tau and KZ effect. Do you need to consider that covariances? Are these two different experiments? So that's why you are treating them as independent?
I think the idea more lies that the tau we would want to constrain at very large scales at very low L values, and the KZ experiments are at L equals to 3000. The only impact we see in the KZ at e power minus 2 tau, but at these values of tau, that is very low. So I think those terms wouldn't affect much.
Thanks.
Okay, any other?
I have missed some part. When you say Pico and Pico BB, is it? Why these two are different? You are not, when you are saying Pico, you are not using Pico BB or only some part of BB.
Oh, okay. So in this combination, I have used the best possible measurements as they will come. Pico plus is the name I have given to this combination of experiments. I'm using the Pico noise spectra in that combination, and for other signals, I use the CMBS4 and Lightbird noise. But
Okay, when you take Lightbird, you don't take Pico, right?
Huh?
When you take Lightbird, you don't take Pico because Pico is much better than Lightbird in every aspect, I guess, right?
By the time Pico will come to observations, Lightbird would have already.
No. I'm not criticizing that. I'm saying that the combination when you take Lightbird, in that combination you do not combine Pico, right? Yes, that is. Yeah, I was just a bit confused with the notation. Sorry. Thanks.
Okay, I don't see any other questions. So let's thank Divesh and move to the last